Graph terminology and the special types of graphs. So we will see some terminology concerning some graphs, and also we will study some special types of graphs that are very known in graph theory in general. We start with the following definition. We will say that two vertices, two vertices U and V in an indirected graph are called adjacent or neighbors if there is an edge that connects them. If U and V are endpoints of an edge in V, simply it is this way. If we have U to be a vertex of some edge and V to be another vertex of the same edge E. So if we call this E, the edge E, we will say that E, the edge, is incident with the vertices U and V. It is an incident with these two vertices it connects. So we will call it incident. And this word is used because it may represent something between the vertices U and V. For example, U and V might be people, phone numbers, and E, the edge between them, represent a phone call. So it is an incident. And we will say that E connects U and V. Okay, good. So we will choose adjacent and neighbors. We will use now what's so-called neighborhood. For every vertex there is a neighborhood. Many neighborhoods may be. Okay. The neighborhood of a vertex V, denoted N of V, this is the neighborhood, is the set of all neighbors of the vertex V in this graph. So what we mean here, say for example we have a vertex V and it is connected to A, B, C, D in here, and this is connected to F, then simply the neighbors of V are the ones that connected to V by some edge. So it is A is a neighbor of B, of V, B is a neighbor, C and D. Okay, now if we have to make it clear, if we have a vertex here, say it is G, then D is not a neighbor of V anymore because G is the neighbor in this case. Okay, good. Now what about if A is a subset of V? A is a subset of V, then the neighbor of that subset consists of the unions of the neighbors of every vertex inside that subset. For instance, if I go back here, let me fix that. Let me go back to the graph and then make more connection. I will say this, for example, is 1, maybe 2. We do that, and maybe this is connected to 3, and this is connected to 4, and so on. And let's fix this. This is the neighbor of V. Now, what if I ask what is the neighbor of, for this graph above there, what is the neighbor of A, where A is given to be the set consisting of V, A, and D. Okay, so we will take the neighbors of V union, the neighbors of A union, the neighbors of D. Okay, And we have the neighbors of V are given here. And then the neighbors of A, what are they? The neighbors of A is V itself, 1, 2, and B. Did I miss anything? And what's the neighbor of D? So these are the neighbors of A, and the neighbor of D are, where is D? They are G and F. Okay. Let's move to more terminologies. So we have seen, for example, so far a neighbor, an edge connecting, above there an incident, adjacent vertices. These are the terminologies of these sections. Now we will go to a new definition where it says about the degree of V. Now the degree of a vertex, let's see what that means. A degree of a vertex, we denoted D of V in an indirected graph. We're talking about here indirected graph, is the number of edges incident with V. The number of edges that are incident with V, that connects V somewhere. Now here, except that a loop at a vertex contributes twice to the degree. Okay, what that means. Now, let's say this is V. Let's assume this is V. And let's assume there are 1, 2, 3, 4 vertices going out of, 4 edges going out of this vertex V. Then we will say the degree of V equals 4. Now what's about the loop thing here? Let's write it here. If we have this situation, V, and is connected to some other vertices, okay, and also it has a loop, okay. Now this says a loop at a vertex contributes twice to the degree. Now the idea is the following. We have a vertex. Once we find an edge connected to the vertex, then we count 1 for the degree. We add 1. Now the loop will be connected to the vertex from both sides, from both ways, from two different sides, right? So we will count it twice. So the degree for V in this graph gives, this is 1 edge, 2 edges, 3 edges, 4 edges, 5 edges. So the degree will be 5. Okay? So the loop counts 2, contributes 2 in the degree of a vertex. So the degree of the vertex is how many edges are connected to that vertex, counting the loop twice. Okay. Some vertices might have nothing connected, no edges connected to them. We will call them isolated. Like here in G, the degree in G of this vertex here, degree of G equals 0. So this is isolated vertex. So a special name for such a vertex. And also a vertex of degree 1 is called pendant. Pendant, mulhaq, maybe بالعربي. Degree of D equals 1. So this vertex will be called pendant. Pendant vertex. Okay. Now in this example, it asks us to find the degree of every vertex. So let's go ahead. What's the degree of A? How many edges are in there? So count 1, 2. So we have 2. What's the degree of B? What is the degree of B here? How many edges connected to the vertex B? Somebody answered 4. What is the degree of C? 4 also. I may miscount, so keep it up with me. Degree of E, how many? 3. Degree of F, how many? 5. 4. Okay, good. Thank you, ladies. Thank you. Good. So the degree, we got the idea. Here are more examples of the degree. We want to make sure we're doing fine. Now, what's the degree of D? Degree of D here. 5, yes. So there are 5 edges connected to D. What's the degree of B? All B. 1, 2, 3, 4, 5, 6. Yes. Thank you. Good, Tanin. I was going to say 5. What's the degree of C? Is 1. Degree of A, 4, and degree of E equals 6. Good. Yes. Thank you for helping me in the counting. Okay, good. So we got the degree. We know what the neighbors now means, the adjacent and the degree. And we will see a theorem concerning that degree. It is interesting theorem. Okay. So let's see what that says. Each edge, now I want you to pay attention to this sentence here. Each edge contributes to the sum of the degrees of the vertices. Because an edge, okay, let me read that again. Each edge contributes to, contributes to, it means it adds 2 values to the sum of the degrees of the vertices. It talks about all the vertices in the graph. Because we have an edge, so I want you to, because this theorem will not be proved, I just will explain the idea of it. Say this is an edge in some graph, edge E. This edge has to be going from one vertex to another. Good? Now, when we count, say this is U and this is V. When we count the degree of V, this edge will count 1 here, will add 1 to the degree of V, right? And also it will add 1 to the degree of U. So this edge, the same edge, adds 1 to the degree of V, and also it adds 1 to the degree of U. So this edge contributed to 2 values to the degrees of the vertices, all of them. Okay, so let's see. Let's complete reading the sentence. Because an edge is incident with exactly 2 vertices, even if it is incident to one vertex, in case the edge is incident to one vertex, which means it is a loop, then it is also contributes 2 to the degrees. This is 1 and this is 2. Okay. Now this means that the sum of the degrees of the vertices is twice the number of the edges. You got that? So every edge will correspond to 2 in the sum of the degrees of the vertices. So I'm not talking about the degree of a specific vertex here. No. I'm talking about the summation of the degrees of all vertices in the graph. Okay? So every edge connects 2 vertices. So every edge counts adds 1 to the degree of this vertex and another 1 to the degree of this vertex. And this applies to all edges in the graphs. And therefore, the number of edges will give you, the summation of the degrees of the vertices will be as twice as the number of edges. Because we said every edge will add 2 to the degrees, okay? So the number of the degrees is 2 times the number of the edges, because we have 2 degrees added for one edge, okay? So this is the theorem. If V is if G is a graph of vertices V and edges E, then an undirected graph with M edges. We are assuming that we have M edges, which means the cardinality of E here is M. Then the theorem says 2 times M, 2 times the edges, will gives the summation of the vertices, degrees of all the vertices in the graph. If you don't believe it for a while, so let's make just a simple graph like that. Okay, so you know that every vertex has degree 3, right? So the summation of the degrees of the vertices where V and it belongs to V, here we mean V consists of A, B, C, D. Okay, so the summation is degree of, that means, so let me write it clearly in details. Degree of A, degree of B, we need more space here. Okay, degree of C plus degree of D, which equals 3 times 3 times 3 times 3, which equals 12. And does that equals 2M? Where is M? What is M? Where M is the number of edges. Am I doing fine here? 1 2 3 1 2 3 1 2 3 1 2 3. Yes, where M equals 6, and that 6 equals the number of edges, correct? Because we have 6 edges in there. This is 1, this is 2, this is 3, this is 4, and this is 5, and this is 6. Correct? Now, this is just a quick example to demonstrate what this theorem says. And okay, so the summation of the degrees equals 2 times the number of edges. Let's see what this question asks us. How many edges there are in a graph with 10 vertices? So we have 10 vertices. Each has degree 6. 10 vertices, each has degree 6. That means if we take the degrees of all vertices and add them, each one of them has degree 6. So we have 6 added to itself 10 times, which is 60. So this is 10 times. And this has to be equals 2 times M. M is the number of edges, and therefore the number of edges, which is M, equals 30. And this is M. Okay. So remember this theorem. The very first theorem we see about the graphs. Okay. Now we have another theorem here. It says the following. In an indirected graph, an indirected graph has even number of vertices of odd degree. So let's understand what that says. We assume we have a graph with vertices, and each one of these vertices has a degree. Now we will look for the vertices whose degrees is odd. Okay, so the question, how many vertices, such vertices there are? The question is, how many vertices we have whose degree is odd? This theorem tells you the number of such vertices must be even. The number of vertices that has odd degree must be even. So we cannot have a graph that has 3 vertices of odd degree. We cannot have that. We cannot have a graph with 1 vertex of odd degree only. And we cannot have a graph of 7 vertices of odd degree. We cannot. The number of vertices that has odd degree that number has to be even. Okay? Why is that? Let's see a sketch for the proof. So let's divide the set of vertices into sets, subsets. Let V1 be all the vertices that has even degrees. And let V2 be the subset of vertices that had odd degrees. So we separated the vertices into two disjoint subsets. One of them contains all the vertices with even degrees, which is V1. V2 contains all the vertices with odd degrees. Now what happened? This summation here, which is equals to 2m, will be split into summations. The summation of the degrees of the vertices with even degrees and summation of the vertices with odd degrees. Now what's happening? This number here is always even, right? Because we assume that this V is coming from V1 that has even degrees. And this number here is odd. Okay, because this V is coming V2 from V2, which has where vertices there have odd degrees. Now look what happened here. The number to the left is even. It is 2m. Okay, so all this must be even. Correct? But look at it. It's a summation of even integers. So no matter how many there are of even integers, if you add them, then the result will be even, right? But this is not the case for odd integers. If you have a number of odd integers and then you add them to get the result to be even, then you have to have an even number of these odd integers, correct? So let me say that again. Let me emphasize something. Since the number to the left is even, it is the number to your left is even, then all this must be even. Now we got this to be even, right? So even plus, then we have to have this to be even, because we have even plus odd does not give me even, which is 2m. So this must be even. This also must be even. This is what I wanted to write then, okay? Now, but it is a summation of odd integers, and this cannot be even unless, so I will say this cannot be even degree V, where V belongs to V2, cannot be even unless the number of terms that we are adding is even. But the number of terms follows how many V's in V2 there are. So unless V2, capital V2, is even. And here we got. So capital is the number, but this is the number of vertices with odd degree. Okay? What we have seen so far are terminologies for undirected graphs. Now we will see some terminology with directed graph, with directed edges. Okay. Directed edges are denoted by this ordered pair U. So we will say U and V. Now this looks like this is an ordered pair. It means there is an edge going from a vertex U to a vertex V. So it is directed this way. It is directed. So we will use parentheses to denote that. And then we will say U is adjacent to V. U is adjacent to V, like going to V. And V is adjacent from U. So from U, an edge is coming from U to V. This V will be called initial vertex. This is the initial vertex. Initial vertex of the edge. And this will be called terminal vertex of the edge. Now this is an edge. When you see that, this means an edge. So initial vertex and terminal vertex of a loop are the same. Again, if we have a loop at V and it is directed, so this will be the same as this point is the initial and the terminal at the same time, the terminal vertex of the loop. Okay. Now we will define a degree of a vertex in diagraph, in directed graphs. And that it is different because at vertex, an edge might be going into the vertex or going out of that vertex. And then we need to count degrees according to this thing. So we will count the number of edges with this vertex as initial vertex, which means the edge is going out of that vertex, or a terminal vertex, which means the edge is going in to that vertex. And this is given in the following definition. We will say the n degree of a vertex phi, the n degree, is the number of edges with the V as their terminal vertex. So it is clear from the definition that it is the n degree. So we will count the number of edges that are going into the vertex V. We will see example here. And degree plus, this is here we used a minus. Here we use a plus. It is the out degree of V, the number of edges that are going out of V, which means V is the initial vertex for them. So okay, let's have fun computing the in degree and out degree of every one of these vertices. So let me go here. What is the n degree? So I will go n degree is degree minus here minus of C. And also answer me what is the out degree, which is a plus here of C. So give me numbers now. Give me two answers. So are you with me? What is the n degree of C? 3. What is the out degree of C? 2. Good. So you counted the loop. Yes. The loop will be counted in and out. Good. All right. Good. What is the in and out degree of F? This is the in degree of F, which is no edges are there, so it is 0. Okay. What is the in degree and out degree of D? Okay, this is just negative, no negative one of D. And what is the out degree of D? Did you compute that? So let me see. 2 and 2. So the out degree, okay, it is 2 and 2. Good. What is the in degree of E? And the out degree of E. So I got answers 3. The out 1, 2, 3. The in 1, 2, 3. Okay, good. What is the same thing for in degree of A and out degree of A? 4, both of them. The in degree is 1, 2 and 4. This is 2, and the out is 1, and 2 and 3, right? Okay, and 4. 1, 2, 3, 4. Yes, they are 4. Thank you for the help. And what's about the in degree of what's left? D. The in degree of this is just negative, no negative 1. The in degree of B, and the out degree, this equals the out degree of B. The in degree 2 and 1. So the in degree are 2. Yes, and good. Thank you very much. Good. Okay. Now, what's about the number of the summation of the number of the n degrees? So look at the theorem below, what it says. So I will keep the graph and the theorem in the same screen. Now look at the vertices of the graph and count the n degree for every one of them, and then add these degrees, and then go back again to the vertices of the graphs and count the out degree for each one of them, and then add all these degrees together. You will find them equal, and they must be equal to the number of edges. Is that it true? The theorem here, do you see it? Do you see this theorem happening? This theorem here, do you see it happening from the above example? And why is that? It says here, the summation of the in degrees is the same as the summation of the out degrees, which is the same as the number of edges. So they are equal. And why is that equal? So the number of n degrees, let's go to every vertex and then count the number of vertices that are going inside that vertex. Why, if we add them all and then we get E? Once you count the n degrees, then each edge will be counted one time, because it is directed and it is an n degree for one vertex only. Right? So you got an idea, Kalthum. Sumaya says when an edge go from a vertex, it enters another one. Exactly. So the edge has two sides. Exactly. Each is exactly, Sumaya, in and out. Every edge has two sides, in and out. If we count the in, then we are counting the vertices. And if we count the out, then we are counting the vertices, the edges again. If we count the in, then we count the edges. And if we count the out, and then we count the edges again. And then why, okay, Mawadda says, why we count the loop only one time? The edges, the loop is counted how many, that's why, Mawadda, the loop goes outside a vertex. So when we add the out degrees, then it counts for one. That loop goes inside one vertex, so when we add the n degrees, then we count the loop again. But we don't add it. We don't add it whenever it is an out to whenever it is an in. No, we count it. Look at the theorem. It says here, we count the n degrees. So the loop will be counted one time. Okay? Now, when we count the out degree, the loop will be counted one time. We will not add this to this, because we are counting the n degrees alone, and then adding all that together, and then count is the out degree alone, and then add all that together. And in both cases, what we are doing, we are counting the number of edges. You got it, Mawadda? Yes. Yes, Sumaya. We counted once as in, okay, and once as out. Thank you. Yeah. Your statement is very clear. Good. Thank you very much. So we got the idea of this theorem. Great. So we have finished that terminology, some terminology concerning undirected and directed graphs. Now we will start the other part of this section, which talks about some special simple graph, some special and very known simple graphs. We will start with what's so-called complete graph. It is called complete because every vertex is connected to any other vertex in the graph. This is so complete, huh? And then we call it Kn, a complete graph on n vertices. We say n because we have n vertices. It is a simple graph, so we have no loops and no multiple edges. That contains exactly one edge between each pair of distinct vertices, one edge. Now for K1, it means one vertex, so we have nothing to do, just a vertex. K2, it means we have two vertices, and then we connect them, we get that. K3 means we have three vertices, and we have to connect every vertex to every other vertex, so we get a triangle. What's about K4? A graph, a complete graph of four vertices. Here we go, four vertices, and we have to connect every one of them to the other. Then we get this K4. And K5, same thing. And keep going. These are five vertices. Okay? And this is K6, makes the idea clear. And every vertex is connected to every other vertex in the graph. So it is called complete graph with n vertices, okay? And it is denoted Kn. Let me emphasize that, with n vertices. Okay, so this is the very first kind of graphs types. If the graph is missing one edge, then we will say it is not complete. Which means if there are two distinct vertices that are not connected by an edge, then this is non-complete. Missing one edge is enough to say it is not complete. Okay, another type of graphs that are called cycles, so clear from their names. Cycle Cn. A cycle may have n vertices. If we arrange them this way, v1, v2, v3, then a cycle means v1 goes to v2. And let me say connected because it might not be directed. V1 connected to V2, V2 connected to V3, V3 connected to V4, V4 connected to V5, and so on till we comes back to V1 where we started, and then we close it. This is a circle. Now here we go, V1 connected to V2. Now you see, I want you to pay attention when we use that this is an edge. This notation, the set notation here, this represents an edge connecting V1 and V2. But a while ago, we used UV, or we may say V1, V2. But this time we are using parentheses. If you now notice why we use this or we use that as sometimes, this is still an edge but it is directed edge, and it goes from U to V, or from U1 to V1. Okay, so be aware of the notation of the edge once the graph is directed or it is undirected. Okay, so V1 is connected to V2, V2 is connected to V3, and so on till we reach Vn minus 1 connected to Vn, and then Vn goes back to get connected with V1. So this is the C3, the cycle C3 with 3 vertices. This is 4 vertices, 5 vertices, 6 vertices. For example, this is V1, V1 connected to V2, V2 connected to V3, V3 connected to V4, V4 connected to V5, and then V5 connects back to V1. So this is a cycle. Okay, a wheel. A wheel. We know what a wheel means. W with n vertices. We obtain a wheel when we add an additional vertex to the Cn. So we have a cycle, but we want to add additional vertex. And this new vertex is connected to each vertex in the Cn, which is simply, if we go back here, these are in blue, give us the C5, right? In here, give us the C5. Now, if we connect this to them, add this vertex here, and connect it to every vertex in C5, then we get W5. Same thing for W4 and W3. So a wheel is putting an additional vertex and connected to every other vertex in the Cn. Okay. Another kind of graphs, which is called n cubed, denoted by Qn. Qn. This is the n cubed. N-dimensional hypercube. We say hyper because it must go for more than 3 dimensions, 4, 5 dimensions, and so on. And this graph has 2 to power n vertices, which represent 2 to power n byte string of length n. A byte string means a string that consists of zeros and ones. And we say we have 2 to power n vertices, and they are represented by strings of zeros and ones. We will see that. See, for example, to make it clear, we start with Q1. We have 2 vertices only, 0 and 1. Q2 will have 2 to power 2 vertices, so we have 4 vertices. And they will be labeled by zeros and 1, 0, 0, 1, 0, 0, 1, 1, 1. Okay? And how we connect the vertices. In here it says 2 vertices are adjacent if and only if the byte string, this is the bit or byte string, that they represent differ by exactly 1 byte position. Okay, let me explain that. We said the vertices will be represented by zeros and ones. Okay, so 2 vertices represented by zeros and 1, they are adjacent if the difference between them is in one place only. In one place, it might be 0 here and 1 here, or 1 here and 0 here. So if the string differs exactly in 1 bit position only, if the 2 vertices are different in more than 1 byte position, then they are not adjacent. Okay, to make this clear, let's go to Q3. Q3 means we have 2 to power 3 vertices, which means 8 vertices. Okay, and how we name them? 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, and so on. And how we connect them? As we said already, when they differ by 1 byte position, then we make a connection. And for instance, let's see here. This is 0, 0, 0. It is connected to 1, 0, 0 because they are different in this position only, the first position. 0, 0, 0 is connected to this because they are different in 1 position only. Okay? Again, why this and this are connected? They are different in the second position only. Okay? Why this and this are connected? Because they differ in 1 position only, which is the third one. Okay? And why this and this are connected? They are different in the second position only. And why this one and this one are connected? Because they're different in the third position only. So notice, for instance, this vertex here and this vertex here are not adjacent because they are different in two positions. They are not adjacent. Same thing for this one here and this one here. They are not connected because they are different in two positions. Okay, so I want you to write, this is an exercise for you, it is in the book actually. Write all vertices of Q4. Okay, how to graph Q4. We cannot because it needs fourth dimension. Okay, but we can state the edges in the following way. For example, the vertex 1 0 1 1 is connected, so this is undirected graph, so I will use this. I will assume it is undirected. It is connected to 1 0 0 1. You agree? Because they are different only in one byte position. And 1 0 0 1 is connected to 0 0 0 1 because again they are different in one position only. So this is the n cubed. This is a special kind of graphs called n cubed. Okay. Another kind of graph is called bipartite graphs. Bipartite graph, which means it is divided in two parts. So that's we say bipartite. It is partitioned in two parts. What are these two parts? Let's say a simple graph. It is simple graph, no multiple edges and no loops. Is called bipartite if its vertex set can be partitioned into two disjoint sets V1 and V1 and V2. So the set V of vertices can be partitioned into disjoint sets V1 and V2 such that every edge in the graph connects a vertex in V1 and a vertex in V2, and no edge connects either two vertices in V1 or two vertices in V2. Okay, so the idea here that the vertex set will be divided, say this is V1 divided in two disjoint sets. Now here says that every edge connects a vertex from this set to a vertex to this set only. No edges goes from vertex to vertex inside one of these sets. No, it's not allowed. It's a vertex from this set to this set. All edges must do that thing. So for instance, if we have these vertices, then we have these edges going this way. Here they're going this way, maybe. One of the edges is not connected. That's fine, maybe. Okay. But we cannot have an edge going from here to here. No, this is not allowed. It will not be bipartite anymore. Okay? Okay. Now, how we find whether a given graph is bipartite? It's not easy in general, but for some graphs we can do it easily. Okay. So again, every edge connects a vertex from V1 to a vertex from V2. V1 and V2 are disjoint, and their union gives back all the vertices of the graph. Okay, now this theorem says a simple graph is bipartite if and only if it is possible to assign one of the two different colors to each vertex of the graph so that no two adjacent vertices are assigned the same color. What that means? Look what I do in this example. I will try to make two colors, okay, so that every edge connects two different vertices or two vertices with different colors, and no edge connects two vertices of the same color. This is what this theorem says. So if I go to C6 in here, and if I color this in green and go color these in red, then I find that I have colored all vertices in two colors only, green and red, and I found that every edge connects two vertices with different colors, and no edge is connecting two vertices of the same color. That means I have partitioned the vertices into different colors or two different sets, and then this is a bipartite. So if I call this V1, and this is V3, and this is V4, that gives me V. I should preserve colors here. If I say this is V2, this is V4, and this is V6, then I get V2. So this is a bipartite graph. Okay. But at the same time, if we look here, K3 is not bipartite. Why? How can I make it? K3 consists of three vertices that we must connect them together. This is K3. Every one is connected to any other vertex. Now, let's try. If I make this green, then I have to make this red and this red, because each of them is connected to the green one. But I found now I am forced that these two red vertices have to be connected, and this is not allowed in bipartite graph to connect vertices from the same set or the same color. So this cannot be bipartite. Now, how to decide? Let's have fun deciding these two graphs, whether they are bipartite or no. Okay. Now, when you are given such a graph and you are asked to show it is bipartite or no, yes, Sumaya, so we may take it as another example. A cycle with even number of vertices is a bipartite. I'm waiting the whiteboard again, it freezed. So let's see that. Let's take it as an example. Let's take, okay, we have seen C6, right? Oh, in general, okay. In general, if n is even, then Cn, the cycle with n vertices, with even number of vertices, is bipartite. And why is that? We will just try to demonstrate this and keep going. So we will give a color for V1, for instance, and then so we will give the vertices with odd indices a color. Okay, and then this one will have the green, which is Vn minus 1, because we are assuming n here is even. So n is even. So this is even, so the one before it is odd. So if we name them this way, V2, V4, V6, and so on, then we could separate the set of vertices into disjoint subsets. One of them contains the vertices with odd indices, and the other one contains the vertices with even indices, and then they will give us a bipartite graph. But if n is odd, then we cannot do that. If n is odd, then Cn is never bipartite. Okay, and try that for C5. See if you can prove it is not bipartite. C5 or C7. We have just seen that K3, which is the same as C3, is not bipartite. No. So given a graph, decide whether it is bipartite or no. To look for such a thing, look at the vertices and try to take the vertices that are not connected to each other. Okay? Take a set of vertices that no two of them are connected to each other. To do so, I will look in this graph and see what vertices are not connected to each other. So my first try will be, I will take A and I will take B. They are not connected to each other. Okay? And D here is not connected to any of them. Good. Now I cannot take G because it is connected to A, neither F, neither E, neither C because it is connected to D or B. So I will take V1 to be A, B, and D. So I'm trying, huh? What about the remaining? The remaining vertices must make the other set because I have two sets only. So if you go to G, F, E, and C, now we will say, oh, okay, it is a bipartite. Now look at the colors. Every edge connects two different colors, and no two vertices with the same colors are connected. So this is a bipartite graph. Okay, let's try to do the same thing with the graph below here. So the idea, I will choose again the vertices that are not connected. So if I start with A, you can start at any other vertex. A is not connected to C, so I will try to take them. I will not take B or D or E or F because D is connected to C. Huh? Okay. So I cannot take D. B, E, and F are connected to A. Okay? So now that makes me or force me to choose the remaining vertices to be the other set. But look, if you do so, you will find there are too many edges connecting vertices of the green color. So that choice was not good. So what else I can do? Shall I just go and choose another choice? Like, okay, I choose A, another vertex which is not connected to it is D. I cannot choose any other vertex. I cannot choose B, E, or F because they are connected to A. I cannot choose C because it is connected to D. So this is my first set. So the other first set has to be this thing. And again, there are too many edges connecting vertices of the same color. So we could not separate the vertices into two such sets so that this graph is bipartite. So this is not bipartite. It is not. So this way you think, so you have you need to keep trying till you give up at some point. Yes, Sumaya here made a good point. In this graph, F is connected to all of them. This is yes. Better? So we cannot separate the two vertices in which the vertices in both subset are not connected. Cannot. Okay. So good. F is connected to all other vertices. So this is a good reason for saying a graph is not bipartite. If you find a vertex connected to all vertices, or you find two vertices that connects to that such that all vertices in the graph are connected to one of these two vertices, and these two vertices are connected together, then this is not a bipartite again. Okay, complete bipartite graph. I believe you will guess what that means. Complete bipartite graph. It is a bipartite with K, M, N. Now we said we have two subsets of vertices in bipartite graph. Now we will care for the number of vertices in each one of them. So a complete is a graph such that an edge between two vertices, there is an edge between two vertices such that one vertex in the first set and the vertex in the other set. That means every vertex in the first set must be connected to every vertex in the other set. Okay? We have seen at the beginning an example of bipartite graph. Let me make an example here, where not all vertices have to be connected to each other. So I will say, okay, this is a bipartite graph. Okay, so this is bipartite, no problem. It does not conflict the definition, despite there are some vertices that are not connected to other vertices. This is fine. Okay, but now a complete bipartite graph says every vertex in one set must be connected to all vertices in the other set. And in here simply says this is Q2, 3, 2, because we have two vertices here, three vertices here, and now every vertex here is connected to all vertices in the other set, and same thing going here. And you can see also that one is K3, K5, because we have three vertices here and five vertices here, three in here and three in here. And we have two vertices here and six vertices here. That's why we say 2, 6. So this is the complete bipartite graph. Subgraphs. Okay. What do we mean by a subgraph? When edges and vertices are removed from a graph without removing the endpoints of any remaining edges, a smaller graph is obtained. So good. Assume we have a graph, okay? And then we want to remove edges and vertices out of that graph. So let me assume we have a graph like that. For example, I'm just making some graph like this. Okay. Now assume I want to remove this part here. I can remove it. Okay. So I will have, after I remove that part, I will have the following. Okay, and what's left after me is that, with having the vertices not being removed. I mean, which vertices not being removed? The ones that, so let's get it from the sentence. So actually this vertex here is the same as this vertex here, but we copy it. Once we removed it, we left a copy back in the original graph. Now, this is what it says here. It says, without removing the endpoints of any remaining edges, because this is a remaining edges. It comes from here. So we did not remove this point. And this is a remaining edge. We did not remove this endpoint. So now we are talking subgraph. We're talking about that. This is a subgraph of that graph. Okay. So a subgraph of a graph E is another graph by itself with a set of vertices W. So the set of vertices of the subgraph H is a subset of the vertices of the original graph. And also for the same edges. So we took subset of edges. Okay? So it is called the proper subgraph if it does not equal the whole graph. So the definition is so intuitive. Subgraph. Okay. Now, one kind of subgraphs here is called the induced subgraph. And this is important. How we get the induced subgraph? I need this. Okay. Given a set of vertices of a graph, we can form subgraph of this graph with these vertices and edges of the graph that connect them. Okay. What it says, assume we have a graph and we want to pick some vertices out of this graph. We take these vertices and take with them the edges connecting these vertices. Then we will have what is so-called induced subgraph. Induced subgraph. And the definition is again here. The induced subgraph induced by a subset. So this is the idea. We are choosing a subset of vertices. So V is the set of vertices, all vertices of the graph. Now choose subset of these vertices, take them out, and take the edges that connects any two of them. Then we will have induced subgraphs W and F, where the edges F contains an edge in E. Okay, so F will consist of edges of E. What edges of E? If and only if the edges that are coming from the graph, both of its endpoints are in W. This is what I'm saying. We have taken the vertices, subset of vertices, and have taken the edges from the graph. Which edges? The ones that whose endpoints were from the vertices we are taking. Okay. Now to make it clear, let's go here. Now this is the graph K5, and this is subgraph of it, but it is not induced. Why? Because we have taken. Okay, let's first show it is indeed a subgraph. It is indeed a subgraph. So simply, the subgraph here, I will make it in blue. So we have taken this vertex and this edge, vertex and edge, okay, vertex and edge, vertex and edge. So we have taken these in blue and we got that. So it is a subgraph, but it is induced by these vertices. No, it is not induced by these vertices. I mean these vertices here. Now take the graph induced by these vertices. So I'm making here another copy of this graph. It is K5 again. So I'm saying I want to take the graph induced by these vertices that I circled by red. That means I will take the vertices and I will take all the edges connecting any two of these vertices. So I will take this edge from here to here, and I will take this, will take that, and indeed will take this, and also I will take that, which is I forgot to highlight above here. Okay, and also I will take this. This was missing from the above graph. I will take it also because it's connecting two of these vertices. And here we go. Here are the graph and the vertices. And now this is called induced by A, B, C, and E. The graph, the subgraph induced by these vertices. Good. And at the end of today's lecture is graph union. If you want to make a graph union, so if we have a graph G1 with vertices V1 and edges E1 and graph G2 with vertices V2 and edges E2 is a simple graph with vertices. Just take the union of the vertices and take the union of the edges, and this is G1 intersect G2. Like this is G1 here and this is G2 here, so we will take the union. So what is missing here? E is not here, so we will take it. And what is else? Okay, and there is an edge coming from this, but it is not here. Okay, and there is an edge coming from this graph, which is not here, which is from E to C. Okay, take the union and then we get that. So every edge here is an edge in the one of the two graphs, and every vertex here is a vertex of one of the two graphs. It is a union. And this is it for today's, and thank you.